time to do so. He has a busy schedule. Like he will actually be traveling to IIT Hyderabad also for next week for a couple of days, again as part of this Distinguished Visitor Program. Just a few words to introduce Sasha. Just want to make sure I get all the dates right. Not his birthday, I don't know that. He's currently, of course, a professor at the ECE department, the Electrical and Computer Engineering department, which is a more common expansion for ECE in the US, as well as the Institute for Systems Research, the University of Maryland College Park. You're also involved in the quantum, I don't know what it is called, quantum IQC or something, is it?
QUICS.
QUICS. Okay. That's also there's a new quantum center at Maryland, which again he's also involved. His research interests include information encoding theory, applied probability, algebraic combinatorics, and quite a bit of late also quantum information encoding. He has received the 2015 Information Theory Society Paper Award, along with his then postdoc, Zach Tamo. He was a plenary speaker at the 2016 IEEE International Symposium on Information Theory in Barcelona. He has served as the editor-in-chief for the Information Theory Transactions. He's currently the editor-in-chief for the Foundations and Trends series in communications and information theory. And this, the latest award that he's got is the 2024 Hamming Medal from the IEEE. With that, I mean, I've known Sasha for quite a long time now, and I first visited him in Maryland when I was there on sabbatical, like about 15 years back now almost. That's when, in fact, I also met Himanshu. So there's, I spent 6 months with him there, and like it was a fantastic experience overall, and like we're trying to replicate that here for him. So that's why we would like to get him to be. So it would be great if many of you can come and have the chats with him and introduce and just exchange whatever work that you're doing, get some, and let him know what you're doing and like get some feedback from him. For students, I think it would be a very good thing to do. So with that, let me ask Sasha to come.
Thanks so much for the invitation. It's quite an embarrassing introduction overall. Yes, it's been a pleasure to come here. It's my second visit, and I'm really grateful for giving me an opportunity to be part of this program. The title, you are seeing it on the screen, and this is all based on joint works with my student Madhura Pathigama. Here is the outline. There are three parts to the technical, three parts of the technical contents after the introduction. One is smoothing binary codes. I will say what this means. Then application. This is still within the same topic to the YTAP channel. Linear hashing and randomness extraction. Again, another application of smoothing. And finally, learning parity with noise. Something about hardness of this cryptographic primitive. All of these are under the umbrella of this smoothing. And here are some references of our preprints with Madhura. By way of introduction, not that we really need this, but theory of uniform distributions originates with Hermann Weyl in 1916, 180 years ago. So choosing a finite set of points in the unit cube for the purpose of numerical integration. So approximate the integral of a function over the cube. Theory of uniform distributions has developed from there in many directions, and I will not even attempt to mention them. In information theory, the most relevant are quote-unquote uniform subsets in the Hamming space, binary space, 0 on to the n, or uniformly distributed points on the sphere, or an extension of that to lattices, which I'm also not mentioning in this talk. So I will discuss this a bit later. Maybe approximate uniformity. Let me move forward. Yes. Well, for instance, what happens on the sphere, again, this is for introduction only. This will not be needed for the main contents of the talk. So on the sphere, in the real space, we choose a finite subset of points, call the subset a spherical code. And then we look at spherical caps, a spherical cap with center here at the north pole, with angular radius theta, or with inner product radius t. T is cosine theta. We choose a spherical code, and then a sequence of codes is uniformly distributed if the proportion of the points in the cap converges to the area of the cap with proper normalizations, right? So a distinctive feature on the sphere is that we can place as many points as we want on the sphere. So spherical codes for a fixed dimension can be of infinite cardinality, so we can consider this limiting procedure. And there is a recent very nice book on this research area. Now, in the Hamming space, this does not happen. If we want the size of the code to grow, approach infinity, then we also need the dimension of the space of the Hamming space to go to infinity, because there are 2 to the n points altogether, and beyond that we cannot go. So for large codes, we need to change the dimension. Right. So let us talk about uniformity from the perspective of smoothing. Let me see if I can move this. Yeah. So we start with the Hamming space. Consider a function from 0 on to the n to the reals. We shall view this function as a quote-unquote noise operator on the Hamming space. Namely, given a function f, this noise operator tr acts on f by convolution. So that's the action of noise operator. Now, we can think of many functions, but the functions that I will consider are characteristic functions of the code, normalized to be probability mass functions. So a code is, of course, is a subset of this space. I will view the code as a probability distribution on the space. So acting by a noise operator on the code creates another probability distribution, in particular if this R is a PMF itself. For instance, given a code C, we act by Bernoulli noise. So here is what we do. We convolve the action of R with the indicator of the code, and this is the output. Or the ball noise. This is a function that takes all the vectors inside a ball of radius t, normalized again, and acts on the code. The task that we wish to pursue is that the output of this noise operator approximates the uniform distribution. So the distribution, this PMF, is close to uniform. And I will say in what sense. But the first remark that is appropriate here is that if the code is small, let's say 1 point, then it is unreasonable to expect that whatever you do with it will be uniform unless your operator is a pure coin toss, which is kind of meaningless for any applications. So codes need to be large to be smoothable, to become uniform. So we are interested on conditions on the code, therefore, in particular, conditions on its cardinality, even more specifically, conditions on the rate of the code, such that acting by a noise operator makes it close to uniform, and applications of this property. So there are some, a sample of works along this line of thought. I will discuss a couple of them, 2 of them later. At this point, just mentioning them. All right, so related topics in information theory. Yes?
So you have a uniform distribution to begin with in a smaller set.
Yes.
You want to perturb it with some noise so that it's a uniform distribution in a larger set.
Yes. Yes, exactly. So this is a particular case of the problem known in information theory as channel resolvability, which was started in the paper by Han and Verdu 1994, titled Approximation Theory of Output Statistics. But these days it is called channel resolvability. So in that problem, this is again a particular case of a more general problem, but we want to approximate a given distribution on the output. So what is your conditional distribution, or if you will, what is your channel, communication channel, that will create the target distribution at the output? This is channel resolvability. A version of that problem, oh yes, and these are follow-up papers that follow that initial work. This is a sample of a larger set. Strong coordination, it is a version of this resolvability problem with maybe sometimes more than 2 terminals. I will not discuss comment on this more. Entropy of noisy functions and decoding on the binary symmetric channel also comes under this umbrella of smoothing. One application of the smooth uniform distributions is for wiretap channels, obviously. Somewhat obviously, because you want the eavesdropper to observe as uniform outputs as possible, not to gain any information. Linear hashing, which is smoothing in disguise. And finally, learning parity with noise. So that problem comes from cryptography. I will discuss it later toward the end of the talk, so let me not spend time on it now. All right, quickly, the wiretap channel, right? Well, it is familiar to the experts, but maybe not to everyone in the audience, so let me spend just a little time on that. This is a particular case of the wiretap channel, namely, the channel I will consider as binary symmetric. So there is a transmitter, Alice, a receiver, Bob, eavesdropper, Eve. Alice and Bob communicate through the main channel, and then information gets to eavesdropper through another channel, which should be noisier than the main channel, or otherwise secure transmission would not be possible. So the main receiver needs to recover messages with high probability, and the eavesdropper should not gain much information about W. So the observation of the eavesdropper is Zn. Mutual information between Zn and W should be less than epsilon. So early works on the wiretap channel were written under the assumption of weak secrecy, namely this mutual information was normalized by the number of users of the channel. Then it was observed that this is insufficient for cryptographic purposes of really hiding the message, because we still leak information. So strong secrecy now is more standard. This mutual information approaches 0 as n approaches to infinity. There is an even stronger notion of semantic security, where we take the maximum on the input distributions of a message W. I will not consider that, but just to mention that it exists. The capacity of the binary symmetric wiretap channel is given by binary entropy of the flip probability to Eve minus entropy of the probability in the binary symmetric channel to Bob. Again, a particular case of the problem, but I'm only considering the BSC wiretap channel. Looks right, no? 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 So it was suggested by Aaron Weiner, the general model of the channel, and he even suggested a scheme for transmitting through the channel. We take a pair of linear codes. Like these days they do in quantum codes, but that was before quantum. C0, C1. So our messages will be cosets of C1 divided by C0. What do we actually transmit? You cannot transmit a coset. So what we transmit is a random vector from the coset. Right? And this scheme with random codes attains capacity of the wiretap channel.
That's when the main channel is noiseless. Bob's channel.
No, this attains full capacity. So there are two requirements, reliability and secrecy. Reliability is that the decoded message of Bob is with probability approaching 1 equal to the transmitted message. And secrecy, I'm rephrasing it here instead of mutual information. I will say that the action of this noise operator Bernoulli operator on the code C0 approaches the uniform distribution on the space. So this is how smoothing enters the Wyatt-F channel, discussion about the Wyatt-F channel. Right. Smoothing of binary codes. So let us give a definition. We say that a sequence of codes of increasing length, n, is asymptotically perfectly smoothable in terms of this proximity to the uniform distribution measured by Rényi divergence with respect to the noise kernels Rn if, well, this Rényi divergence between the noisy version of the code and the uniform in the limit is 0. And we can define this for all orders of this Rényi divergence. So if P is 1, this is the KL divergence, Kalbach-Leibler divergence. But we can use all the P's from 0 to infinity, both ends included. All right. So what is the Rényi divergence? Of course, this is the standard definition. This is expectation of this Radon-Nikodym derivative, dp dq to the power p minus 1. This is nice to say, but impossible to compute. And before we say what this means, so in the finite discrete case, this derivative is nothing but p divided by q. So we take the expectation of that with respect to p. That's why the exponent of p is 1 greater here, divided by p minus 1, and that's the definition. Now, a remark to be made here. As p increases, this is a progressively more stringent requirement. So it is more uniform if this dp approaches 0 for larger p. Infinity is the largest, the best possible. For p1 is the KL divergence. And of course, if q is uniform, then dp is related to Rényi entropy. So here is a summary of expressions. If p is 0, this is nothing but probability of the support of p, log of that. This is KL. If p is anything but 1 or infinity, it is this expression. For 1, we get KL divergence, and for infinity, we get max of the log of the pi divided by qi. All right. P norm over random variable is nothing but the expectation, but what is important for us is to write this expression. So given a probability mass function, dp between f and the uniform can be written as the p norm of this random variable 2 to the n f. So this is easier for analysis because we can use various norm inequalities. And the same for infinity. So smoothing can be therefore written in terms of the p norm. We take the noise operator, act on the indicator of the code, take the p norm, and the limit is 1. This 2 to the n is an artifact of the definition of the norm of this expectation. All right. Uh-huh. So we choose code words or messages for transmission uniformly. Sorry?
You don't add any extra randomness to it? Like the uniform over the coset also, right?
No, cosets come later. We are not discussing cosets. This is just the smoothing problem as such. That comes later. All right, so we have choose a uniform code word, act by the noise operator. That creates a new probability distribution. We want that close to uniform. Okay, smoothing of codes.
So, perfect code, and all the, supposing it has radius t, and all of those are equivalent, that gives you uniform distribution.
It will, but perfect codes, luckily for me, don't exist. And therefore, there is something for me to study. But yes, it will. Yeah, so the balls are of size 1 or 2, right? And that's it. But close to perfect codes will do approximately that and so forth. But you're quite right. Also, even more than that, the name escapes me. What is it called? The not completely regular. There was some. Well, you know what I'm talking about. No, that is graphs. The codes. Well, something, yeah, around perfect codes. We even have this in the paper, even though it does not fit into the context of our study, because ours is mostly asymptotic study. All right. So what can we do? We find the smallest rate at which the codes are smoothable. Threshold rates for binary codes to achieve asymptotically perfect smoothing under Bernoulli noise. We also have threshold rates for the Ball noise, and we have bounds for the wiretap channel, Reed-Muller codes, Y-Reed-Muller codes. I will explain somewhat later. So Reed-Muller codes, of course, achieve capacity of the binary input symmetric channels, and it would be reasonable to assume before you start looking at that it would also achieve capacity of the wiretap channel, but we didn't manage to prove that, and in fact, from discussions with various colleagues, even those involved in this proof Reed-Muller capacity, it looks a difficult problem. So something for you to look at. Prove that Reed-Muller codes achieve capacity of the binary BSC, wiretap BSC channel under strong security. Looks a difficult question. So we proved that they achieve something, but that something, the rate is less than capacity. All right. Polar codes achieve with weak security, that's from Magdovi Vardy. Later with Talo Gulchu, we proved that they achieve strong secrecy, but that requires shared randomness. So again, not quite a clean proof that one would wish for. Right. So what are thresholds for perfect smoothing? Here is the state of the art. Define the capacity as the smallest achievable rate for DP smoothing. As we said, the rate has to be large. If we start with the entire space, then it's already smooth. So we start shrinking it. At some point, it will break down. When does it break down? Here is the answer. So for P between 0 and 1, it is the Shannon capacity of the BSC. For P1 to infinity is 1 minus HP, the P3 entropy. So results from 0 to 2 and infinity were known in the literature, Lei Yu and Vincent Tan, but we proved the cases from 2 to infinity. And that's not a direct extension, in fact. That required quite some effort. So this is Rayleigh entropy, which I will use for the plots. So this is almost the 0 entropy, except the 0 would be a box, which is difficult to plot. This is H1 Shannon entropy, this is H3, this is H infinity, so it becomes smaller and smaller as we increase P. And so here are the capacity plots. This is smoothing for P0 to 1. This green one is smoothing for P equal 2. This is smoothing for P infinity. So we impose more stringent requirement on approximating uniformity. We have to pay by increasing the rate. All right, and this is something that we prove. So this is achievability is proved with random coding. Are there explicit codes that achieve these bounds? This question is somewhat similar to achieving capacity of the binary symmetric channel, and in fact this similarity can be even pushed a step further, because as we know, to achieve capacity, there is this gap to capacity expressed in terms of the length. So as the code length increases, the gap to capacity in terms of the rate is inverse proportional to the square root of the length. That is one of the basic results of even early works from Strassen and then Polanski, Poor, Verdun. The same for smoothing. So approaching capacity from above or approaching the threshold from above imposes this gap of 1 over square root n on the rate of approach. So that is why, by the way, these polar codes here, well, I shouldn't be spending some time on this, but I will nevertheless do it. So why didn't manage to prove strong secrecy? The reason is that in order to make it secure with polar codes, we need not only to include the perfect bits, the perfect channels, we also need to include intermediate channels for strong secrecy. But including intermediate channels ruins the communication part of the story. So therefore, they stopped short of doing this, and something else was needed, this shared randomness, to circumvent that. Right. So how do we prove that theorem? For the for attainability, we use random coding. That's not so, maybe not so interesting. But for lower bound, this involves some work. Ultimately, we do induction. So how do you induction on P when P is a real number? Well, you do the following. You split the real line from 2 to infinity into segments of length 1. Take your P to be rational. And then you show that if you have this smoothing for 2 to 3, you can do the induction step from 3 to 4, and generally from P minus 1 P to P plus 1. So induction on those segments for rational P's, and then of course use the density argument to establish this for all real P's. So that is the smoothing threshold. Which codes can achieve perfect smoothing? The first remark is that achieving capacity of the binary symmetric channel does not guarantee perfect smoothing for the reason that I just mentioned, that there is a gap from below and by the same token a gap from above. So if you achieve capacity of the channel, you approach this threshold from below. If you want smoothing, you need to approach it from above. So more is needed. Polar codes achieve perfect smoothing. Reed-Muller codes, not quite. They achieve a certain rate, which is, so this is really the rate achieved by Reed-Muller codes. And with D1 smoothing, we should be here on the blue curve, but we are here on the yellow. So there is a gap to where we want it to be. Again, we were not able to prove that. And the way this result is established is riding on the fact that Reed-Muller codes achieve capacity of the erasure channel, and using some considerations from recent works, but in particular by Alex Samorodnitsky, where he established some connections between the binary erasure channel and the binary symmetric channel, which are way too technical to discuss in this talk, but let me just mention them. Right. So I have 2 slides, but I don't think I should stop on here. Let me just mention these works that we used, Alex, and then the work by Jan Hasla, Alex, and Orias Berlo on translating erasure correction into error correction and finding the proportion of errors correctable by Reed-Muller codes, in particular on the binary symmetric channel. This result was quickly overshadowed by the capacity achieving result, but they did prove a very interesting statement by considerations that are completely different from later tools used for capacity achieving. All right. Reed-Muller codes. So what happens on the wiretap channel? Now we can discuss this, right? So on the wiretap channel, we wanted to show that Reed-Muller codes achieve capacity, and well, we didn't manage to do that. So this is the this is capacity. This is the smoothing rate for codes that achieve, let's say, Reed-Muller codes, which is above capacity. And as we said, the capacity is the gap between the rates, between the capacity of the wiretap channel is the gap between the capacities of the eavesdropper channel, of the main channel and the eavesdropper channel. And so let us fix the binary symmetric channel for the main channel, let's say 5%, for the eavesdropper channel 30%. So the capacity is computed as 0.59, and looking at the rate achievable by Reed-Muller codes, which is computed as a difference between their smoothing rate and the something else for the eavesdropper channel, we get 55%. So we stop 4% short of attaining capacity, and well, I leave this as an open question. Right. As I said, it does not follow from the capacity achieving proofs. There is another very interesting approach where classical quantum duality. So for every classical channel, there is a well-defined notion of a dual classical quantum channel established in the work of Joseph Renes and also studied by Narayanan Rangaswamy and Henry Pfister, Rob Caldebank. It almost works, except for it is very difficult to figure out how to do proper measurements on the quantum side for the decoding of those Reed-Muller codes, which is apparently, again, a difficult question. So these two things, which were kind of obvious, don't work, and well, this is open. All right, let's switch to universal hash families. What is this? So we have a source that follows some probability distribution. And I will look for the ground space will be fq to the n. So because I want linear hashing, so finite field of q elements, n vectors over that finite field. The source, the distribution of the source is unknown. This f, the family of functions, let's say from f2 to the n to f2 to the m, even though later I will use fq, forms a universal hash family if we choose a random function out of this family, the probability of collision is at most 1 over 2 to the m. So m is the range of the function. Right? So rather there are 2 to the m vectors in the range, and we want collision to be at most 1 over 2 to the m. A classic result is this leftover hash lemma, which says if m is less than the infinity entropy of the source minus log 1 over epsilon, then the total variation distance between what really? Between f of z, this is the hash function that we choose, and the f itself, so this is the joint distribution, and the product distribution uniform and the distribution of f is at most epsilon over 2. Right? So this is the classic result, and in fact we can rewrite this total variation distance, of course, is the L1 norm, proportional to the L1 norm. So this can be rewritten in terms of the L1 norm as shown here. Epsilon over 2 changes into epsilon because of this 2. Okay, and then it was strengthened by Charles Bennett in 95 and co-authors to the second Rényi collision entropy, second Rényi entropy. It can be written as follows: if the expected KL if the m is less than the second Rényi entropy minus log 1 over epsilon, then the expected KL divergence is at most epsilon divided by ln 2. Right, and so what we do, we motivated by these p norms and p divergences, we did the Rényi divergence guarantees for linear hashing. So yes, for p norms and linear hashing. So far we haven't mentioned linear at all, but let us look at linear. So we have a source on fq to the n. Our functions will be linear codes. So how do you use a linear code as a function? Very simply, you take the parity check matrix and multiply your source vector by the parity check matrix, so you compute the syndrome of the vector. Those syndrome are random, of course, because the vector z, the source itself, is random. And so we start with pz, and we end up with distribution h times z. Z is a column vector, h is a short, long matrix. There are more columns than rows, right? So this is a smoothing problem as such, right? So we can use this smoothing idea to establish Rényi guarantees, Rényi divergence guarantees. Here is what we prove. If z is a random vector about which we only know the entropy of the source, there are no assumptions about the distribution of the source, no memoryless, nothing else, just the entropy of the source is known, then the expected dp divergence is bounded above as shown here. This is a more stringent guarantee on linear hashing, derived using these ideas of smoothing, and well, we can rewrite this conclusion, and this also shows that the probability of the hashed value is almost independent of the code, if you look at this inequality. And as we said, this is a stronger guarantee for linear hashing. Among previous works, let me mention the work by Masahito Hayashi and Vincent Tan. They proved P uniformity for memoryless sources. So they need memorylessness. For the derivations, we only use the assumption of entropy. So this is a more general result of sorts. Right, remarks on the proof. Well, there is a technical lemma, or theorem, if you will, that says something about the probability of, we take a random code vector, add a z, the source vector sampled from the distribution pz, compute the expected p norm of that vector for random linear codes, expectation over random linear codes. And that is at most the right-hand side. That again involves some technical work that probably will not discuss here. So XC is a uniform random code word. So this is really a technical result that after that can be translated into the hashing claim. Well, there was some previous work on this largest hash bucket. So what is the expected number of vectors that collide, they have the same syndrome. So these papers, including some recent work, they were looking at this expected size of the worst collision in this linear hashing. Related problem, not exactly this one. And they also assume uniform sources on FQN. We assume an arbitrary source with a known entropy. We cannot, get rid of this obsession with Reed-Muller codes. So let's look at an explicit family. What can we accomplish if we take Reed-Muller matrices for linear hashing, right? Not random codes, but now something explicit, because after all, we want an explicit set of functions. Well, then this is again related to attaining this smoothing rate of Reed-Muller codes. And there are results proven here. If the rate is bounded below by something, then we attain this hashing requirement using matrices of Reed-Muller codes. Right. The last part is learning parity with noise. A different problem. You may have heard of learning with errors for cryptography, that is for lattices. Learning parity with noise is the same question, except that it is for binary codes. Why do we care about this problem that I will define momentarily? Well, it underlies several cryptographic primitives: symmetric encryption, public key cryptography, in particular Alekhnovich's system, collision-resistant hashing by Zwicker-Brakersky, and you forgot the first name, I'm sorry. So the problem is this. There are 4 parameters, k, delta, and alpha. And there is noise rate, delta, sample complexity, and success probability. So we are given a collection of samples. A, I, M is the message. So M is fixed throughout. AIs are random vectors of dimension k. The BIs are random bits. So M is chosen uniformly out of k-dimensional vectors and is fixed. Our goal ultimately will be to find M. What do we see? Well, we choose AI and BI. AI is uniform, BI Bernoulli delta, so this is the noise rate. And find M with probability of success at least alpha. All right, so we're observing many samples. We need to find M. Learning parity with noise. This is almost a decoding problem if you think of it a little bit. And so the question that was asked once those cryptosystems were proposed, there's always what's cryptanalysis, right? Is it computationally hard, or maybe LPN is easy and cryptosystems will be broken? And they don't know, but they thought of proving hardness of LPN by reducing decoding problem to it. Decoding problem is kind of well assumed to be hard. At least we know NP hardness claims. This still does not mean much, but it means a little something, more than nothing. So worst case decoding problem is defined as follows. We have a matrix K by N. Think of this as generator matrix of the code. A vector which is a received vector, G times the message plus the error for some message and some error, and the weight of error is W, exactly W. So we have this promise that there are W errors. Find M such that Y is Gm plus E for some E. And well, this M may or may not be the same as M dash, but we hope it is. Finding an efficient solver for LPN would amount to constructing an efficient probabilistic decoder for linear codes. So if there is an efficient solver, then we kind of break the hardness of the decoding problem, but maybe that is not possible, therefore LPN is hard. All right, so how do you convert LPN solver into a decoder? As follows. So we sample M dash uniformly from F2 to the K, find the probability distribution P on F2 to the N such that the total variation distance between GZ, so this is this, yeah, and E transpose Z, and uniform and Bernoulli is at most epsilon, where Z is our vector chosen according to P. So we have found this probability distribution. Now we sample many ZIs out of P. So this is our sample complexity. AI is GZI, BI is E transpose Z, and then we write Z GM dash plus GM plus E. We call ZG, we call it A, M plus M dash plus BI. And then we submit these pairs to the solver. If the solver finds M plus M dash we know, so we have found M. So that is the reduction. And if N epsilon is less than alpha, then our algorithm outputs M plus M dash with success probability alpha minus N epsilon. It is not a deterministic decoder, but a probabilistic one. And in fact, if N epsilon is small, then the success probability is the same as the success probability of the LPN problem. Right? So with probability alpha minus N epsilon, the message M is found in time T. This is the solver's complexity, times some polynomial in N and K. So that is the reduction. And the question has been whether a meaningful reduction was possible. By a meaningful reduction, we mean the following. So first, let us say what is the bias. Bias, there is a Bernoulli random variable, probability of 1 delta. Bias is half minus delta. Okay. So the bias of our noise rate up there, this one here, is too small if it is 1 over polynomial of K. K was the dimension of the vectors in the LPN problem. If it is declines faster than the polynomial, if it is 1 over omega 1 over the polynomial, then this supports symmetric cryptography. So we want this bias. And we want the total variation distance between these distributions to be less than epsilon, which is nothing but fast smoothing. So fast smoothing and reasonably large bias would support a reduction. And our result is that there is no such reduction. So this has been pursued in the computer science community. They were hoping to do this, to attain a reduction, but this is a negative result. It shows that this is sort of a dead end. It is, with all these probabilities, this is not really a complete rule out of the possibility, but this is a serious argument against the possibility of this reduction. So a meaningful reduction should satisfy. I'm discarding this pair of distributions from this total variation distance. This distance is smaller than this one. So if this is less than alpha over n, then this is a necessary condition for a meaningful reduction. And the bias, as we said, should be omega of 1 over polynomial of k. Zvika Brakersky and co-authors showed that meaningful reduction are possible for vanishing code rates. Yu Zhang and Thomas Debrien-Lazare and Nicolas Resch showed similarly with additional assumptions on codes and smoothing distributions. And it was not clear whether reduction with constant rate was possible, which is something we wanted to establish. So using these smoothing ideas, we show that the necessary conditions do not work, so reduction is not possible. Specifically, we show the following. Suppose there is a sequence of linear codes of rate r, which is positive, so non-vanishing. Dual distance is positive, which is not much of a constraint because most codes will satisfy this condition. So for any sequence of random vectors, there is a sequence of error vectors such that if the total variation is lit low of inverse polynomial, then the bias is also lit low of inverse polynomial. So we want this to be small, but then this is small, which is bad for the reduction. And in particular, if this is exponentially small, then even the bias is exponentially small. So this is against the possibility of the reduction. We also show that slow smoothing supports reduction. Well, slow smoothing is not something you want for that problem, but to be honest, we need to do that because why is slow smoothing bad? Well, slow smoothing results in the following. The probability of success of the decoder is alpha minus n epsilon. But if epsilon does not, if the smoothing is slow, epsilon is large. That means that the success probability of the decoder is degraded. And so even though that reduction is possible, this does not really tell us much about the hardness of the LPN problem because after all the decoder will result in error more than success. Right. So that really ends the presentation. This is thanks for your attention, and maybe one or two sentences in summary, right? So this smoothing is simply taking a code, viewing it as a delta distribution on the space, putting a sum distribution on top of it, looking how uniform the outcome is. There is a threshold rate for smoothing, so we cannot smooth small codes. Large codes are required. Thresholds are established for different orders of Rayleigh divergence. This applies to the White-up channel, even though for Reed-Muller codes we stopped short of getting where we wanted to be. This applies to linear hashing, and this applies to learning parity with noise. So a couple of applications of smoothing to convince you that the problem is somewhat meaningful, even though we are not discussing communication problems here. So codes for something else. That's it. Thank you. Yes.
And so what is it about Reed-Muller codes that is helpful here?
Yes. It is the following. They attain capacity of the erasure channel, and that in fact imposes powerful conditions on the codes. That has been highlighted in this line of work by Alex Samorodnitsky. It basically shows some rather but very technical conditions for their uniformity, specifically for the entropy of noisy functions created from read-Muller codes. So code sequence that attains capacity of the erasure channel, but this is pretty much the only families that we know. So this additional uniformity contributes to the smoothing properties of these codes, and to their performance on the wiretap channel, and to their performance in the linear hashing question.
So it's not related to some algebraic property?
No, no, no.
Group or anything?
No automorphism. The automorphism, of course, is used for the erasure channel, but no, this is some entropic properties of the codes. I had that lemma on the slide, but I thought it doesn't make much sense to try to discuss it here.
How would you define the wiretap channel for in the quantification?
There is a definition which I don't remember, but yes. Oh, later, right? Okay. Yeah. No, but it has been done a very long while ago.
So, I mean, in the case, so it looks like, I mean, one observation seems to be that, like, if you have a family of codes that attains this maybe strong secrecy capacity of the wiretap channel, then it is also, that will give you an achievable rate for smoothing.
Yes. Well, rather backwards. From achievable rate for smoothing is good for the wiretap channel.
No, the other way around. If you know that there is a family of codes that achieves the capacity of the wiretap channel.
Yes. I think we can do that.
Strong capacity.
Yeah.
Then, secondly, but then, well, okay, no, I think also that you're looking for, a distribution. So here, I think what you're, at least all these results seem to only imply something for the wiretap channel in which the main channel was noiseless, because if you have a
No.
I thought you would need some smoothing on the larger code, on the, so that is a smaller, you're taking the smaller code and then like some smearing that with noise, and then you should get a uniform distribution on the larger code.
Yes.
Is that not right? Or,
That sounds about right, yes.
or is it, you're just looking at cosets of the smaller code within the larger code, right?
No, but I can assure you this is for the noisy main channel. Noiseless is exactly when they couldn't achieve smoothing. That's why they dropped it, because for polar codes they had to inject those intermediate channels, and they lost the communications and the communication part while attaining secrecy.